Yeah, so I think that the notion of questioning boundaries is really something that we've been doing internally in the office. We've been practicing for about 25 years now. Over the last couple of years, we've had to kind of radically rethink what we're doing and why we're doing it. And this is, I think, something that many architects are starting to face. And in part, what we're recognizing is that a lot of the work we've done before, which we thought was motivated for all the right reasons, may have actually been heading in directions that were not entirely as effective as they could be. We've always been interested in adaptive reuse, working with existing buildings, whether it's an art museum in Texas or a former maintenance building in California that gets converted into an open collective office space, reusing as much as possible the materials that are there, or even in interior renovation projects, a new museum in New York City, where we adapted an existing space into a large-scale kind of exhibition space for a museum for posters. Much of this work, as many architects have been focusing for the last couple of decades, has really been privileging questions of the energy performance of the building. So in this science building at Cornell University, we took a 1960s building that had almost no insulation, didn't work particularly well from a operation carbon standpoint, and really spent a lot of kind of thought and detail and design on the performance of the envelope, rethinking this building with terracotta, with solar shading, with the kind of processes to make the building more energy efficient. But we begin to realize, and have realized over the last couple of years, that this is not exactly the whole story. So if we kind of put this work in the context and what we do in the context of the kind of global picture of the kind of climate crisis, these are all things we know, right? So that we're at a state, we're releasing way too much carbon, producing or carbon gases, and this is having major effects on the climate. Our current policies are insufficient, and more importantly, we really need to be in a position where we're reducing CO2 significantly by 2030. It's only 7 years from now to get to a point where we're net zero by 2050. The tricky thing here is that even though buildings, as we know, account for a large portion of global carbon emissions, most of the energy, and I'm talking about design energy, has gone towards operational questions. How do we make buildings more energy efficient, et cetera? But that's led to a kind of interesting condition where now, based on how we currently build buildings, typically, about half of the carbon of the footprint of a building between now and 2050 will be split between the operational carbon, and the other half is really in the upfront carbon that the carbon used, the energy used to make the building in the first place. And this is something that's been understudied. Again, most of the focus has gone towards energy efficiency, the role of the performance of the building, but we've not been taking seriously the nature of the materials that go into the building at the beginning. And the problem with it is that quantity of energy, that quantity of carbon is even greater the better performing our buildings get, in part because often high performing buildings require a lot of metal and steel and solar shades and various devices. So in a weird way, in the act of getting more efficient for their operations, they've gotten less effective for their embodied carbon. So it's offset this even more. And then that carbon is, as we know, spent up front, right? So you basically release that amount of carbon at the beginning of the building. And right now, that's when we need to be starting to make these savings. And whereas the operational carbon will take years to build up to their level of equivalence, right? So we need to be transforming the nature of how we build, what we build from and with, and as a result, use those new materials as a way to kind of rethink what we're going to do. And in part, one could argue that, we can just work with reuse. We should look at buildings and cities as material banks. We should kind of just work with what we've got. And the problem with that, even though that's something that we've been highly invested in, it's not going to attend to the fact that there's going to be this global demand for building that's going to continue, right? Something like an anticipated projection of 25 trillion square feet of new buildings, largely in the global south, for new construction. So we can't just reuse our way forward in the future. And it raises very fundamental questions about the legacy of modernism that, frankly, most of the building industry around the world is still invested in. The use of concrete, steel, and glass. These are carbon-intensive materials. They tend to be based on linear extraction, where you make the building and then you trash it at the end of its relatively short life. It assumes global supply chains where we're going to ship materials all around the world, and we don't tend to take into consideration the environmental degradation to where these materials are extracted, as well as the toxicity associated with these materials when they actually get embedded in our buildings. And also from a standpoint of kind of conceptual presence, it tends to put the architect as a kind of consumer, a kind of selector of products, as opposed to really engaging the full life cycle of a material. So we would argue that this is a radical possible change to the very nature of the discipline. Thinking through biogenic and geogenic materials, not only are they lower carbon or carbon sequestering, but they produce a different relationship between the materials and design and the kind of life cycles that need to be part of the agency or what the architect gets engaged in. In part, we know that this is because materials they don't have equal relationship to carbon. Glass, steel, metals, and concrete have extremely high quantities of carbon associated with their mass, whereas other materials, plant-based materials, have the capacity to sequester and store carbon in the very building itself. So how do we move to the bottom end of the spectrum, the sequestering materials rather than the emitting materials? So this was the basis of this book that Matthew was talking about, Manual Biogenic House Sections, which was just released a couple of months ago. And what we wanted to do with this is try to gather the best examples of buildings from around the world that have used plant-based and geo-based materials as a catalyst for their design, which is to say these are looking at really inventive, creative design projects that use these materials, not just local traditions or indigenous traditions, but really looking at how design can actually be a catalyst for the seduction and the performance that can come with these materials. What was crucial for us is to make sure that we were showing buildings that are built, that exist as physical examples. And in a strange way, as much as we acknowledge that houses are not the perfect model for building in the future, we should be building multifamily housing, we should be looking at more collective ways of inhabiting the earth. The single family house is actually more of a problem than a benefit. It works as a really good example for how architects have tested out the use of these materials in built examples, and then we could actually then draw these. So one of the book starts with actually a critique of the single family house. Looking particularly in the United States, this house has gotten to be extremely big since the end of World War II. The standard house in the US was about 1,000 square feet in 1950, and it's ballooned up to 2,500 square feet, in part because the materials are quite cheap. Added to that is the fact that these materials are often made from petrochemical basis. They tend to have just toxicity associated with their entire life. But their cheapness and has made them ubiquitous. They're everywhere within the building itself. So one of the things we do in the book is kind of trace, where do these materials come from? What are their problems? How are they installed? Where do they end up at the end of their life? And almost all of them end up, not surprisingly, in the landfill. The other thing that we kind of looked at and we kind of critique is the assumption that architecture or buildings are largely built out of multiple materials, right? So if we look at the standard wall section of a conventional house, it's actually an assembly of multiple materials. These lightweight, thin, what we call single performing, they only do one thing often. They're the weather barrier, or their structure, or they're the insulation, or they're the paint. They do just one kind of purpose, often because they can be marketed for that purpose and legally justified for that purpose. These tend to be hygienic layers. There's an attempt to make everything about the building be as clean-based as possible. And not surprisingly, they produce a strict boundary between the interior and exterior. You don't get gradients. You get this kind of, this is on the inside and it can be conditioned and controlled, and this is on the outside. And really, so much of what architects end up focusing on, unfortunately, is just that final thin veneer, the siding on the outside or the paint on the inside. And the space in between is often, particularly the insulation, is often left under considered. So we wanted to shift that focus in the book by looking at buildings that were thick, that were mono materials, that did multiple things, that were, in some cases, looked at how one material could be used to produce every performance characteristic within the project, from structure to insulation to weatherproofing to waterproofing to siding to interior finish to even acoustic and in some cases olfactory benefits. And so we felt it was important to actually use our skills as architects to draw these, to make these legible. So the 55 houses in the book were all presented in 9 different chapters based on the dominant material they use, plus a chapter on reuse, which we still think is super important. And each chapter introduces the material, introduces the range of carbon associated with that material based on published databases, carbon databases that we footnote. We then map through the translation between the field and the form. So how do you go from a plant or an earth-based material to construction? What happens at the end of the life? How could we start to produce more kind of circular kind of economies within this system? And then also looked at just simply what are the logistics about the translation of plant to product? Like, what are the ways in which commonly these materials are formed, and what are the steps along the process? Arguing that the goal here is not to present these as exhaustive or thorough, but really to give a sense of what the dominant models are, so that architects could start to think about what other ways that we could translate these plants into building form. Each of the houses were presented through photographs. Not many of these, I should say very few of these houses are well known. Unlike the manual section, there was a previous book we had published that was all about largely canonical, really well-known buildings, and we wanted to make those visible. These are less known houses, and so we wanted to show them with photographs, exterior and interior, construction photographs to show how they were put together, as well as exploded axonometrics to show how the project came together. But the most important drawing was the single cross-section perspective that would show at a fairly high level of detail the material assembly, how it was put together, what the spatial consequences, and then what the spatial or environmental context this house existed in. So in parallel to the manual, and I'll show you examples of the different materials and the houses that we drew relative to that. Last summer, we spent a fair amount of time designing 5 houses that we wanted to look at relative to specific materials, but to really push those materials towards architectural or spatial ends that would take seriously the idiosyncrasies, the unique qualities of each of these materials. In other words, to not simply see plant-based and earth-based materials as a replacement for modern kind of logics and material, to not just simply say, okay, I used to have plastic insulation, now I'm going to use hemp insulation. But what would happen if we actually looked at the spatial consequences that could come out of these materials? Could we end up with very different assemblies, different approaches to the very nature of the house itself? So I'll weave these 2 things together for the rest of the talk: the manual of biogenic house sections, and then also the 5 houses that we designed, speculative houses that we designed based on these assembly and the overlaps between these different materials. So mass timber is kind of the poster child for plant-based building material. It's now quite well established. And it's, on the one hand, it's a fantastic replacement for concrete and steel, structural capacities, carbon storing, et cetera. But there are some problems with it. not the least of which is that it takes a long time for trees to grow. Harvesting trees, in a sense, takes that carbon sequestering component out of the forest. It actually releases as much carbon as it might sequester. And then we have the added problem that the lumber industry often uses only about 50% of a tree. So 50% of the harvested tree is going to go back to the atmosphere anyway. So at most, it might be a net zero gain. So it's not the single solution that many people argue it to be. Yes, wood is fantastic. It's much better than concrete and steel, but it's not the only solution. And so we have to look beyond simply mass timber as the sole solution. The other problem is that often mass timber relies on a high amount of glue. Many of these glues are bringing in petrochemical-based additives. There are biopolymers that are and bioadhesives that are I think the future, but at the moment many of the adhesives are coming from sources that have toxicity associated with them. The other problem with mass timber is that typically it's just a replacement for the post and beam logic of steel or the kind of slab logic of concrete, precast concrete. And in some ways, we would encourage different modes of thinking that take seriously the sheet slab quality of the CLT. Jennifer Bonner has done excellent work on this, both with her book Blank, that does exactly that, argues for the role of the sheet good as a source of invention, and her own work, House Gables, is a great example of a kind of house that uses the CLT to produce very different forms that echo the gabled form of the timber two-by construction, but produce spatial nesting that is fundamentally dependent upon the qualities and the unique characteristics of CLT. Another project in Finland, which was on the cover of the book, is this kind of fascinating project that's almost exclusively built with cross-laminated timber. It's really two skins of cross-laminated timber, a rectilinear skin on the inside and a more faceted skin on the outside. And the interstitial space between them is essentially a kind of an insulation space that's not packed with insulation, but is a kind of buffer zone of air. It's a very different way of thinking about how we construct. It has a huge amount of carbon sequestering, in part because there's not the need to fill all these cavities with incredible amounts of plastics or rock wool or other form of highly carbon intensive insulation. So this building itself sequesters about 48,000 kilograms of CO2. So for a project that we entitled CLT A-frame, we were interested in how you could actually use the entire CLT blank, the entire 10-foot by 50-foot unit of CLT. In other words, to not have any waste associated, not have any cutoffs, not have any of the kind of excess, but to take it on as a kind of component itself. So this house is formed by 10 panels of CLT. The two pair of panels at the back of the house are laterally stabilized by a series of staircases, whereas as you move towards the front of the house, those two blanks then lean into each other, forming the iconic A-frame of the weekend or the country house. At the back of that house, the stair extends up and it keeps going up onto the roof deck. And the space between these parallel panels then becomes a kind of roof terrace that then leads to a lookout in the treetops at the front of the building. And on the inside, as we know, one of the great things about CLT is it doesn't require any interior finish. You can use the wood itself as the finish. You don't have to have all the plaster. You don't have to have the latex paint. You don't have the gypsum board as an interior finish. But we particularly like the fact that you would have this now almost 50-foot high space, a very unusual section that's the logical consequence of just using the entire sheet good of CLT. So the other material that needs to be looked at for its structural capacity is bamboo. And unlike wood, bamboo grows extremely quickly. Takes about 3 to 7 years to come to full maturity. You don't clear cut bamboo forest, you tend to kind of take out about 1/5 of the bamboos. It's rhizomatic, so it continues to grow. You're not damaging the root system. So it's a continually able to be harvested. So it doesn't involve the clear cutting that timber does. More often than not, the culm is used by cutting it into a series of fragments and re-gluing it together. But one can also look at ways that you don't have to simply kind of cut it into these different strands, but you could actually use it as a bundled culm. It produces some questions about the relationship between the irregularity of the structural component and how it can be aggregated into a system. But there's some fantastic examples of the way in which this bundling of multiple culms can produce a kind of inventive structural approach. Here, a house where the very lashing or the kind of triangular bracing, diagonal bracing of the culms actually produces a very different approach to the nature of the floor plate. Here you get a continuous ramp working its way through the house that also provides lateral bracing across the whole span. So this is an incredibly strong project working with the ability to use bamboo strength to weight ratio and the spatial qualities that might come out of that geometry. Another project, Anna Herringer's hostel project, youth hostel project, where the bamboo is used to produce a diaphanous screen, a really unusual kind of architectural form that produces a gradient of inhabitable layers. The inner layer is a rammed earth with kind of cantilevered sleeping areas, and then you get this very unusual structure as an exterior kind of skin shading device that really is a product of the unique characteristic of bamboo being able to be bent, but also itself quite strong. Earth is a fantastic material. It's been around a long time, right? Earth has been a building material for as long as we've been on the planet. And it unfortunately hasn't got as much attention as it deserves. It really has great capacity to operate as a kind of thermal envelope, as a kind of protective barrier, be able to be extracted or basically harvested, if you will, from very local sources. It can be, because it's really a translation between a liquid material that then solidifies, it can be formed into earth blocks or tamped into rammed earth walls. Again, the hope is to not use as much Portland cement, but work with a clay mixture to allow that to stabilize the wall itself. And there are recent experiments that are looking at 3D printing with earth itself, not with concrete. Again, most 3D printed houses one sees are based on printing concrete, but there are ways to think about 3D printing earth that I think are incredibly exciting. So in the Von Haus Fleury house, here you're looking at about 30-inch thick walls. These are cob walls, so a combination of earth and straw that are basically kind of stacked up and then sheared simply with a spade or with a shovel to produce this really beautiful contrast between these earthen walls that do absorb humidity, have fantastic acoustical qualities, are great in terms of their ability to work as these massive walls for all those qualities, and they have an interesting contrast with the wood floors and ceilings. These wood floors and ceilings themselves are infilled with straws and insulation, and they actually overhang the earthen walls substantially in order to mitigate some of the erosion that would occur through wind-driven rain on the exterior of the building. But these earth walls are then not just your interior finish, but also the exterior finish of the building. And in the process, able to sequester a fair amount of carbon. It should be noted that in this particular building, the earth is packed, or the cob walls are packed around a wood framed wall that is really carrying the load. So often it's a hybridization between these different materials to produce these inventive solutions. I wouldn't argue that a single material has to do everything, although there are examples I'll show where that is the case. So a block project, an earth block project in Burkina Faso by Carré Architecture looked at locally making many kind of thousands of bricks that were then used to produce the walls, but also formed into low arches They themselves were then protected with a thin veneer of corrugated metal that helped protect against erosion, but also helped harvest the water so that this could be used as gray water for the project. And a 3D printed earth project from outside of Bologna by the 3D printing company WASP in conjunction with Mario Cucinella Architects is really a kind of fantastic experiment in 3D printing earth. Again, not concrete, not Portland cement. This is pure earth, and it's printed in a series of bands that allow there to be cavity spaces within these relatively thick walls. Again, these are about 30-inch thick walls that are then infilled with rice husks for the insulation. So it's a kind of inventive process where geometry, material, insulation, and performance all start to line up together in this single inventive project. So for a project, for a kind of a type of an agrarian or a farmhouse, we wanted to combine earth-based construction with the efficiency of bamboo to produce a kind of lamella bamboo or an arched bamboo larger scale structure in which we would then position an earthen dwelling. The lamella structure is based on using the exact same relatively short length of bamboo, 8-foot length of bamboo, that then using a repetitive joint is able to produce an entire kind of diagrid or a lamella that then forms the entire large scale single span column free space. The north side of it is clad in thatch insulation, whereas the south is built with translucent polycarbonate, plant-based polycarbonate, to, in a sense, produce a quasi-interior, a type of a greenhouse, in which then there would be located the earthen structure embedded partially in the ground. So this introduces gradients of temperature as part of the project. So it's not a binary between outside and inside, but it assumes that you have this kind of using the building as a kind of an insulation layer and then inhabiting that insulation layer, using that as a greenhouse, using that as a kind of space for different ways of producing climactic qualities within the project. And ultimately producing a different model of an agrarian structure that doesn't just default back to a pre-engineered steel or plastic structure within our landscapes. So the last three materials I'll present are all based on thinking about insulation as a point of departure for their use. Architects are not really good about caring about insulation, to be honest with you. We tend to want to have enough insulation to fulfill a performance criteria, and as long as it's inexpensive, that tends to be the driving criteria: performance and cheapness, right? The downside is that it's led to now most insulation being produced by plastics, and we can think about ESB, XPS, blown insulations, et cetera, or even mineral rock wool, mineral wool, which is basically a kind of very peculiar way of essentially aerating rock through a huge amount of energy and heat to produce this material. Hemp, on the other hand, is plant-based. It's from the hemp plant that grows incredibly quickly. It takes about 3 months to come to full maturity. And the hemp plant is a very resilient plant. It tends to require very few pesticides, can work with relatively limited quantities of water. In other words, it doesn't require a huge amount of irrigation. And more importantly, the plant itself can be used in multiple ways. Hemp, at least in the United States, was basically banned kind of unintentionally because of the war on drugs. It's a different, industrial hemp is very different than the plant that grows, that's used to produce the psychoactive drug that we know in marijuana. But by banning marijuana in agricultural fields, in a sense, the entire hemp industry got killed, at least in the US, and has only been legally possible since 2018 to actually grow in the States. So this is a kind of new emerging material, in part because growing the plant has only been legal for about 5 years. So there's an interesting process of decortication, the separation of the plant from, it has many components, but really we're talking about a separation between the fibrous exterior of the plant which can be used to make textiles, paper, et cetera, versus the interior hurd, which is really what gets used to produce the insulation in buildings. It has a whole series of air pockets, which is why it's able to work as an insulation material. But hemp is often combined with lime to produce what is known as hemp lime. It's unfortunately often referred to in English as hempcrete, which suggests it's a replacement for concrete, which it's not, right? It's an insulation material. It's not a load-bearing material. It can be sprayed into the wall, and the lime combined with the hemp produces a fire-resistant, rot-resistant, insect-resistant material. It can also be formed into prefabricated panels. One of the downsides to hemp and lime is it takes a fair amount of time for it to dry. So prefabrication deals with that delay, that drying delay that might be difficult on site. And there are also companies looking at ways to build it into prefabricated blocks so it can be stacked up within the project. Cork is another insulation material that actually does even more things. In some ways, it's even more robust than hemp. It can be structural, it can be acoustic, it can actually be rot resistant, it can be moisture resistant, et cetera. The downside to cork is really a question of scale. It takes a fair amount of time to grow the cork on the tree of cork oak trees, only be harvested every so often. More importantly, there's only a limited region in the world, the Iberian Peninsula, where most cork is grown. And so it's very difficult to scale cork at the level that it would need to become a kind of key building product. Most cork used in construction nowadays is a product of the waste of making wine bottle stoppers. And most of the cork we currently use is used to make veneer, so flooring. But one particular example, a kind of fantastic house, was made almost entirely out of cork. This involved milling about 1,200 custom cork blocks. Cork is able to be milled very well, so that here the cork is able to do all of those things I described before. Almost the entirety of the house, with the exception of a series of lateral ring beams, was made out of cork and corbelling cork into the roofs. Amazing house, and again, the only downside to cork is that it's harder to scale it as a material. In contrast, straw is everywhere. It is everywhere in the world. Wherever cereal grains are grown, straw is the agricultural waste product of that growth. So wheat, barley, rice, etc., all produces straw, and an incredible amount of biomass around the world is actually produced every year now in the form of straw, but it then gets returned back to the atmosphere by burning, decomposing, et cetera. So this is a fantastic resource. It's available, it's cheap, it's already there. It doesn't have to replace any other agricultural fields. We need to figure out ways to use straw, in part because it actually is much more resistant to animals and to insects than one would think. If it's sufficiently compressed, it can be fire resistant and it can be load bearing. So and of course it has insulation capacity because of the nature of the straw, the straw geometry. It grows really fast and is ubiquitous. And it's currently able to be used in a variety of different standpoints, but I think that there's an entire future of how straw could be used that goes beyond the current models. Those current models are often dependent upon either harvesting it as thatch, and that's kind of a slightly different type of reed than the cereal-based straw that we see being formed into the bales. And one of the interesting things now is because the harvesting of straw to make it able to be removed from the fields and used and distributed back to animals as bedding for animal agriculture, is that it's formed into these 2-string or 3-string or round bales. This is purely a product of the way in which it gets harvested, not necessarily the best way to use it for building. Nonetheless, it still gets used this way. And there are examples that go back to Nebraska, the plains, the Great Plains of the United States, where there are limited trees, where buildings were built from stacked straw bales. clad in plaster to provide a rain protection against insects. And also the structural skin, the skins out of plaster can become structural, deal with lateral loads, particularly when combined with some level of mesh. It's embraced by the California building codes. California, a fair amount of seismic constraints. So straw bale is acceptable within those seismic regions. Often it gets infilled into wood frames, gets infilled into wood frames or can be prefabricated into assemblies. And what's nice about this is you can actually compress it even more. And the more you compress straw, the more it's resistant to the spread of fire. It basically chars, it doesn't burn. And certainly if you compare it to any other plastic-based insulation that burns incredibly quickly with toxic association, straw is so much better as an insulation material than any of the plastics on the market. There are some great examples of load-bearing straw being used to produce an entire building. So Atelier Schmidt's experimental pavilion, the Gardas Pavilion, stacks up jumbo straw bales. These are quite big. These are 650 pounds. They had to be moved by a crane, but because they're so dense, they could carry the load. The only additional structure in this building is a lateral ring beam of CLT that stiffens it from side to side. Otherwise, it's a corbelled structure that basically encapsulates the entire building in a thick blanket of agricultural waste that also works as a high-performing insulation and humidity absorbing or mitigating skin. And this building, then sequesters 84,000 kilograms of CO2 equivalent. It's a pretty amazing project for a small project. So this idea that we can use straw, use its cheapness en masse is something we're super excited by. So we designed two projects, and I'll end with these two. Designed two projects that said, okay, there's a different way to think about thickness, about poche, about the nature of a building where we don't assume that the appropriate approach is to make this super thin, multiple material plastic wall. What happens if we could imagine a much thicker wall, a more interesting way to approach the space of the house? So for this project, we combined both the efficiency of CLT volumes or modules with the thickness of straw bale. So in a sense, we took almost assumed the entire building was solid straw, and we carved away space by then infilling those spaces with prefabricated four-sided CLT modules. In a sense, using the CLT to displace the straw and replacing that void with then an inhabitable room that would be prefabricated through CLT. And CLT are tied together to form a kind of diagonal structure. So that stabilizes the straw, and then the straw helps stabilize the CLT. So in other words, these two things work in conjunction with each other. There's a large CLT overhang roof that provides mitigation against the rain-driven erosion, and also provides shading around the house. So what you end up with is a series of rooms, almost like kind of Adolf Loos spiral or ROM plan of rooms working their way around the central atrium. That really allows every room to have full floor-to-ceiling glass, and at the same time, the building is thick and fully insulated. So we're trying to maximize both. Lots of openness and air and access to light, but also thickness and porosity and density. So hopefully getting at a very different understanding of the nature of the architecture because of the unique qualities of straw. And another project, which we titled Mass Straw as a intentional kind of counterpoint to mass timber. Here we looked at two different ways to assemble straw into architectural form. One would be this long wall that was based on stacking up a series of straw bales and starting to corbel them a little bit to introduce a kind of space. That would then be placed in parallel or adjacent to a thickness of straw that then cascades along a hillside. So both of these bales of straw are working on a topographical site and register the topography in different ways. They're then connected or tied together through a series of wood joists that are then infilled with again, straws, insulation. And then we like the idea, there's often a criticism that, animals are just gonna eat the building. And, it's a nice anecdote. We know the story about the three little pigs. So straw comes with bad PR. We understand that. But we also kind of want to kind of embrace that. You know, what happens if we actually did put a layer of straw on the top of the building on top of the waterproofing layer that would be left to return back to the ground? And could we actually make this so that animals would want to come to the top of the building? You could embrace the fact that animals might eat part of the house, and that's okay. So to find, again, different ways that the building can be part of the landscape. On the inside, we wanted to both stack up the straw to produce a different landscape for the domestic space, the collective domestic space, the living room, the kitchen, the dining area, but then also to sequester the private spaces into the thickness of the straw within the project itself. So here you get the collective kind of gathering space for the family or who's living here. This is a very small house in some respects. I think it's only about 800 square feet. And then the rooms themselves, the bedrooms are small. They're embedded into the cocoon of straw on the back. They have skylights, so they bring in light in a different way. And you end up with a house that actually has more mass, more solid straw than it does occupiable space. And we really like that idea. We like the idea that this modernism's avoidance of the thickness, trying to make building as thin as possible. What happens when we went the other direction? Could we actually embrace thickness and poche and the carbon storing capacity of that as beneficial to the architectural logic? So I'll end there, but really what we're very excited by this as a kind of radical transformation of the very premise of what we do as architects, of the very nature of design. We think this is probably the most significant catalyst for transforming the basis of what our architecture is built from since modernism. But I would argue that we're at the very early stages. This has to accelerate, it has to scale quickly, and it requires inventive approaches to how one would start to work with these materials in other ways. So what I'm presenting is not the end, it's not the conclusion, it's the catalyst, it's the start, it's the way, and the challenge to you all is to think about how might you work with these materials in ways that creatively envision a better future. So thank you very much.